And also at the same time, I'd like to talk about green AI, because I think that's a very interesting topic right now. And I think that, yeah, it combines, you see that it's a perfect combination. And also specific for New Zealand, because that's, I think that's one of the main features of New Zealand is this care for the environment. So, yeah, as Charlie mentioned, I'd like to introduce you a little bit about what's the TAIAO project. So what we do, this is a project funded by MBIE, 7 years, but this is with University of Auckland, Canterbury, Wellington, and also Becca and Med Service. And yeah, the main goal is how we can use AI in environmental science, how we can use data science to improve how we do environmental science. And yeah, I think that's really, really perfect for New Zealand, in the sense that as if you ask anybody about overseas about New Zealand, they will always imagine this paradise that is green with all of these nice yeah, these nice pictures. And so I think that's something that yeah, it's very important to keep New Zealand a green environment. And also at the same time, I like to talk about green AI, not only in the sense that we work with environment, but also how we do AI, right? So we can do AI spending a lot of resources, or we can do that using a small amount of resources. And I think also New Zealand is perfect for that, because there is this number 8 wire mentality. The idea is that, yeah, let's try to be smart, and let's try to do things using the small amount of resources. And I think that, yeah, this number 8 wire is a perfect example of that. So as you know, yeah, AI is becoming very, very important, especially after November last year, when ChatGPT was released, and now everybody's talking about AI and how AI is going to be really, really changing everything, and that could be something like internet, could be an important revolution. So yeah, for this time, ChatGPT was really fast in taking, in having 1 million users. So that was something that never happened before. So there's always, things are much slower, but this time it came very, very fast. So yeah, I think it was, yeah, in 5 days, yeah, ChatGPT was able to get already 1 million. And yeah, it's changing how we do things. So we're thinking of AI as something that was coming. And I think that now everybody knows that AI is already here. And yeah, we need to be smart on how we use this technology. So what I'm going to try is to first explain a little bit what is AI and what is not AI. And then from there, I'll see how we can use AI to solve sustainable challenges. And that's the TAIAO project. And then I'd like to also mention about how we do AI in a green way, how we can do AI not using many resources. So to start, what is AI? So the AI, there are many definitions. I think at the moment what we can see is that AI is a better way to do computer science. It's and let's say an automated way of doing computer science, right? So it's a really computer science on the steroids. So it's how we can do these automations in a much faster way. And you can see that in terms of popularity, yeah, since the release of ChatGPT, AI has increased its popularity. And yeah, it's many people. So for example, Donald Knuth, so he's one of the most prestigious computer scientists. He is already saying that, yeah, well, basically computer science is going to be renamed machine learning, in the sense that, yeah, if you want to do cool things right now in computer science, you need to be doing that on machine learning and AI. So there are many definitions on AI. So I really like this one. So that's the one from the European Commission, and it's very simple, but I think it's going to be very helpful to understand what AI is and what AI is not. So AI is a collection of technologies that combine data, algorithms, and computing power. And that's, I think, is the key, because this is what we need for AI. We need data, we need algorithms, and we need computing power. And this is going to give a lot of insights on how we can do AI and how we cannot do AI, and what are the risks and challenges of AI. So let's start with data. So at the moment, all the technologies on AI are mainly based on data. So we can see that, yeah, we are generating so much amount of data continuously. And that maybe that's the reason why we are talking about AI right now, and we are not talking about AI 10 years ago, 20 years ago, is because now we have a lot of data and a lot of computing power to process this data. So that's what makes the difference. And of course, it's not a coincidence that the organizations that are leading on AI or the countries that are leading on AI are the ones that they have more data. So let's say that we can see that the core of AI is data. If you don't have the right data, you are not going to have the right AI. So AI is based really in data. So and that's why it's very important to understand that when we are talking about AI, we are always focusing on how to get the right data. So just to mention Harari, the author of the book *Sapiens*, yeah, he said that if you want to make a country colony, don't send the tanks in, just get the data out. So it's really important right now. The data is something that if you have control about the data, you have control about everything. And this is something that also that applies here in New Zealand, where there is, yeah, from the Maori perspective, data sovereignty is really important. And this is why, yeah, Mahelona from Te Ipu Media says that, yeah, data is the last frontier of colonization. So again, it's very important to understand that data is the most important thing in terms of AI. Okay, so now we have the data. So now how we analyze that? So how we use it to extract information and to make predictions or to create new things. So that's why the algorithms are this important factor. So let me show you some examples. So imagine that we have a website. We are working in New Zealand, and we have visitors to the website, and we want to predict if a visitor is going to be a customer or not. So how we do that? Well, mainly the standard way is that we have someone that has a lot of experience, and then they can make their predictions with domain knowledge, no, if someone is going to be a customer or not. What about if we have the data? Then we can try to make an algorithm and create a model that is the one that is going to be able to make a prediction. So in this case, yeah, we have the data points, and there are customers and non-customers. And then given a new point, a new visitor, we want to detect if this is going to be a customer or not. And we're going to do that based on the data. So let's start by the most simple way to do that is, okay, we look at what is the majority visitor. So in this case, we see the majority visitors are non-customers, so we make the prediction is a non-customer. Very easy. We are not learning many things, so it's very basic, but we always need to compare with that because at least we need to be as good as this. Then, of course, we can try to improve that. We can have a linear classifier. Basically, it's a line, no, where we separate between customers and non-customers, and then from that we can decide if the visitor is going to be a customer or not. Another model that we can create is the nearest neighbors. So the idea is that, okay, let's look at the similarity. So we see what are the nearest visitors and take the majority class of that. For example, in this case, we look at the two nearest neighbors, nearest visitors, and then we predict the class of these visitors. For example, in this case, they are customers, so we predict that's going to be customer. We have decision trees. That's the nice thing of a decision tree, that is very easy to understand how the predictions are going to be made. For example, in this case, yeah, we can decide if it's from North Island or South Island, and then the North Island which region, and then we can see that yeah, we have a prediction for each one of these. So it's the nice thing of these decision trees is that we really understand how decisions are made, right? And this is very, very important when we are making decisions to really be able to explain how these decisions are made. And yeah, way to improve that is instead of having only one model, it's having a combination of different models. And this is what is called ensembles. And for example, there is this famous ensemble that is called random forest. Basically, the idea is that instead of building, we are going to combine decision trees, but instead of combining perfect decision trees, we are going to combine random decision trees. So that's the easy way to do that. And finally, deep learning. So yeah, as you know, the big thing right now on AI is mainly based on deep learning. So and deep learning is based on these neural networks. So let me give you an example. So imagine that we are detecting images. The problem with images is that then we don't know what are the features that we need to use. So yeah, imagine in this case, we want to detect if an animal is an elephant or a penguin, a kangaroo. So how we are going to do that? So, well, we need to find some features, right? And then based on the features, we are able to decide if this is going to be one animal or not. The problem is how we detect this feature, right? So how we are going to do this feature. And then this is why these neural networks are so useful, because they can do that automatically. So what these neural networks are going to do are going to build and find these intermediate features that are the ones that we are going to decide when we make the classification. Yeah. And finally, yeah, in the case that we don't have labels, so we don't know if they are customers or non-customers, what we can do is that we can group that, and then this is something that is called clustering. And there are different methods, like k-means and DB-scan. The idea is that, okay, what we do is that we put all the similar visitors together, and from there we can yeah, make some predictions. Okay, so now, what we can do and what we cannot do. So data is really, really important. So for example, imagine a self-driving car. So what we can do whatever was in the data. So for example, if we can predict, yeah, we can detect cars, we can see what are the cars that are coming, everything that was in the data, it's perfect. We can do it. What we cannot do is things that were that yeah, they were not in the data. For example, yeah, imagine that in a self-driving car, we have a person that is starting making signs. If it's only one or two, yeah, we can, the model is not able to learn. So yeah, that's the limitation right now. So the limitation is that everything is based on data. So if we need to improve that, we need more data. And until we don't have more data, we are not able to do that. So this is why if you look at these self-driving cars, what they are doing is basically getting data, so that over time they can improve what they are doing. Okay, and then finally computing power. So yeah, this is one of the main challenges. We are building all of these big models, but these big models are very, very expensive in terms of energy. So for example, yeah, that was 4 years ago, that creating an AI can be 5 times worse for the planet than a car. But yes, still we are getting worse and worse. So this is the new ones with last year with GPT-3. So we can see that, yeah, if a car is 63, building GPT-3 was 500, and this is not GPT-4. So you can imagine that the amount of energy that we are using is really, really increasing. And the reason for that is because the models and the data is bigger and bigger. So the size of the models are increasing exponentially, and the data that we are using also is increasing. So that's why, yeah, we are using a lot of energy for that. And yeah, so now that I explained a little bit what is AI, now we can see, for example, ChatGPT, what it is in terms of this definition, right? So if you look at ChatGPT, basically it's a lot of data with a very smart algorithm, and a lot of computational power. So this is what is basically ChatGPT. Okay, so what is the data? We don't know. This is closed. So it's interesting. This is OpenAI, but in this case, it's closed. We don't know what's there, and this is why the new legislation in Europe is trying to not allow this. So we really need to know what's in the data used to build the model. And yeah, the algorithm. So it's using this new transformer architecture, and it's very interesting that the algorithm is basically predicting what's the next word. So yeah, and then what is getting is a probability distribution of what is going to be the next word, and then from that it makes this prediction. So this is what is this large language model. This is what is based on this transformer architecture. The most interesting thing is that that's not only that, ChatGPT also has this reinforcement learning from human feedback. And this is really important because this is the one that allows it to do a lot of mistakes. The previous large language models were doing a lot of mistakes. They were not polite. They were saying a lot of things that were not really, let's say, not correct, but also at the same time they were not could cause a lot of trouble. So the nice thing of this reinforcement learning is that it's helping to avoid these cases. So still there are some cases and these models, they hallucinate, but it's getting, it's really helping to improve how this is done. Okay, so yeah, so that was some explanation on AI. So now I'd like to talk specific about TAIAO. Yeah, I think it's a project that started in 2020. And yeah, I think it was really interesting at the time because that was before the pandemic, and then everybody was talking about that climate change was the biggest challenge of the time. Still, I think it's that. So some people would say that there are other big challenges, but I think still climate change is one of the most important ones. And yeah, the TAIAO project, what it's doing is basically creating fundamental data science. So we create new algorithms, new methods, but also at the same time, we want to provide tools and to grow capabilities, and specifically have applications, case studies in environmental science. So yeah, the team is heterogeneous. We have researchers, machine learning, data scientists, environmental scientists, software engineers, and we are dealing with a lot of different data sets, large, special, and temporals. We have different work packages. One is on time series and streaming, so on evolving data. And then we have another work package on extreme events, and another work package on deep learning, how we analyze images. And yeah, in terms of the benefit for New Zealand, so yeah, I think that the core is that we really want to deliver excellent research. So it means that we need to do something that is done in fundamental data science, environmental science, that is excellent internationally. So this is our main goal. We are very interested in growing capabilities of the next generation of researchers and developers, and in both sides, in data science and in environmental science. And yeah, and one of the main goals is how to grow these collaborations, how we really make everybody work together so that we can improve what we do. And yeah, and finally, we would like to also to give effect to the Vision Mataranga. So in terms of what we did, so we have this nice community website. So this is, it's TAIAO.ai. You go to the website, you will see that we have different things. We have data sets, we have notebooks, we have software, and then we have discussions. So the idea is that we are not storing data sets, but what we are doing is that we are a catalog of different data sets. Yeah, you can find there all the data sets with the different descriptions and how to access that. We have the notebooks. So this is our notebooks in Jupyter. So the main idea of notebooks is that we have in the same document, we have the source code, documentation, and results. this is really, really convenient in terms of data science. And the idea is, yeah, it's really to have this link with the data sets and notebooks so that people can use this to improve how they do data science. We are working also on a specific software. So we have this River software. This is a new Python software for streaming data. So this is data that is evolving over time, and that we are not storing the data. We are processing examples by examples. I'll talk about this later. We have this species identifier, this species classifier. So this is specific for New Zealand. And this is something that we have the website. We have also an iPhone app, and we have an Android app. And you can see the idea is that we take a picture, and then we get what's the predictions of what is the species. And then also we have some panel where we can understand the explanation of why the model is predicting that a specific species. We have been working also with NVIDIA on the speeding up machine learning models with accelerated Weka. So the idea here is to Weka in principle is not using GPUs. So the idea was to have an accelerated Weka that was able to use GPUs. And this is a collaboration that we did with NVIDIA. One of the, I think one of the contributions that we want to have in this project is this data mesh architecture, to use this data mesh architecture in applications. So the idea is that instead of having all the data analytics centralized in one place, we like to have a data distributed data architecture. And for that, we like this data mesh architecture. So what's the idea? The idea is that we are going to consider data as products. Okay, then each data product is going to have a domain owner. We're going to have a platform that is going to serve all of these data usages. And finally, we are going to have this federated computational governance. So what's the idea here? The idea is we would like to have something that is efficient and something that is distributed at the same time. And this data mesh is a really new concept that appeared, I think, 3 years ago, and that is really based for big data applications. So this is something that is being applied in finance, in big organizations with a lot of data, because it's the most efficient way to do things faster, but also having less mistakes than having everything centralized in one place. Okay, and then in terms of the projects that we are working, so one of the main focus is explainable AI. So we are working on how to explain methods. We really think that it's not only, we have all these models that they give the prediction, but it's very important to have an explanation, because if we don't have the explanation, these models may be doing mistakes, and we need feedback to check that everything is working properly. So this is why explainable AI is really, really important. The thing right now is that there are many, many different methods on explainable AI, and we are interested in see what are the best ones and how to get the most of this technology. We have this collaboration with the Forest Flow project from Science. The idea there is that they have these sensors in this forest, and they would like to analyze that on real time. So what we are doing in this case is we are applying this data mesh architecture there, so we can have all of these data that is analyzed in real time. And we are using this machine learning for data streams and time series to see how we can get all of these predictions on real time. We have another application of this data mesh that is this flood impact prediction. So this is a project with Waikato Regional Council, and we are using data from them and also data from MedService. And the idea is to have a system that is able to make predictions on floods. How we do that? So the idea is that we get this data from rain radar from MedService, this data from Waikato Regional Council. We consider these as data products in the data mesh. We get the data, and then we use this to make the prediction and then to visualize in a dashboard. So yeah, I think that that's a nice application on where we can use these technologies. For predictions, we started using LSTMs, but now we are already starting using time series transformers. Another application is in deep learning, where we look at, in this case, we look at invasive C-star detection through hardware. We're looking at C-stars, and the idea is that we don't have too much data. And the idea here is to use this weak supervision to be able to find that. So again, this is something very useful, and also it's good because it's based on explainability, so we can understand how these models work. Another project is this machine learning for algal bloom detection. This is by University of Auckland and Shera. So the idea is that, yeah, the traditional way to detect algal bloom is going to the lake and measure that. So the idea is, can we use satellite images to do that? So that's the idea. So the idea is how we can use machine learning so that we save having to go to the places to measure. We can have these measures, these estimations using detecting from images. So in this case, yeah, we have these images from the lakes, and we would like to detect where there are algal blooms. So the idea here is to use the semi-supervised learning and multi-task learning to be able to do that. And finally, another one is on extreme events. So we like to measure these marine heat waves and to get predictions on that. Yeah, this is something that is quite challenging. The data is complicated. So you see that in many applications, we need to spend a lot of time with the data, because the data is really the one that we need to get it right. But still, we have so many algorithms and methods that we can deal with when data is not perfect. In this case, for example, in this case, data is imbalance. There's a small number of observations. So yeah, we can use different algorithms. In this case, we use this graph neural networks, and that's a way that we can use to build these models that then we can use to make these predictions. And this is from University of Canterbury. Great. So yeah, that was more or less some of the projects that we're working in TAIAO. Yeah, maybe now I'd like to finish talking about how we can do machine learning in a green way, how we can do that in a more efficient way. And in this case, yeah, it's very interesting that this, what we call incremental learning or streaming learning, is perfect for that. So let me show you, yeah, this an example. So the standard way to do machine learning is that we have all the data in one place. That can be in memory or in disk, and then we build the model, and then we use this model to make predictions. So that's the standard way. So what's the main problem with that? First, that we need to have all the data in one place. And the second thing is that the data needs to be static. The data cannot be changing over time. So for that, when data is changing, the standard way to do that was to train a model periodically. So let's see, okay, we are going to train the model every week. And we are going to use the data of the last month. Okay. So what's the problem of that? The problem is that, yeah, we don't know how often we need to retrain the model and how much data we need to use in the model. And that depends on the change, right? Because if the change is every day, it does not make sense that we build the model every month. Or if the data is changing every month, it does not make sense that we build the model every day. So yeah, these are the things that make this difficult, and this is why this data stream approach is quite good, because it's deciding all of this in an automatic way. So the idea is very simple. So instead of storing the data, what we are going to do is that every time a new example arrives, we are going to update the model, and we are going to do that continuously. So this is, yeah, this data stream approach. So the nice thing is that it's very efficient. And the second thing is that it's adaptive. So if things changes over time, the models are going to be change over time. So for example, imagine we have a decision tree. So if there is change on the decision tree, the branches are going to disappear, new branches are going to be created, everything is done automatically. So yeah, these are the main properties of streaming machine learning, and this is why it's, yeah, I think it's very useful, is because it's very efficient in terms of memory and time, and also is adaptive. So if there are changes on the streams, this is going to be solved automatically. As we are dealing with a lot of data, sometimes we're going to be happy with approximate solutions. So if computing the exact solution will require, I don't know, 1 week of computation, and we can have something that works in seconds, we'll prefer something that works in seconds. So this is why what we say is that, yeah, we're going to have a solution with a small error epsilon with high probability 1 minus delta. So it means that we are going to be happy if we have a small error, if with this, we really, really speed up how we do things. And usually the nice thing is that we can decide the size of the error, right? So we can really, really choose small errors. So yeah, let me show you an example. So imagine that, yeah, we want to store in 8 bits. We want to count. Imagine that we are counting events, but we only have 8 bits. So how many events we can count in 8 bits? So we compute that exactly. This is going to be 255. But that's very interesting because that was the first paper on streams. The idea is that there was this counting large number of events in small registers by Bob Morris. He was able, only having 8 bits, he was able to store 130,000 events. That's a huge amount. So how he was doing that? Well, basically the idea is that instead of storing the number, we store the logarithm of the number. And the way to do that was very, very simple. So the idea is, the standard way is that we have a counter, and every time there is an event, we add 1. So if we want to have an approximate solution, instead of adding 1 always, we are going to add 1 only with probability p. So it means that we toss a coin and then we decide when we add 1 or not. And that's the nice thing, is that doing that, what we are storing is the logarithm of the number. And this is something that has been used by, for example, by Facebook. There's these famous counters that they use to compute the degrees of separation of all the users in Facebook. So imagine the number of users, and then you want to compute the average of the distance of each user to all the other users in Facebook. That's really, really a large amount of computation, but using these approximate methods, they were able to do that in a very, very efficient way. Yeah, that comes from this experiment from Milgram in the 60s that he did this experiment in the US, and then to send one letter from one coast to the other coast of the US was, it needed 6 persons. So the degrees of separation was 6. But now, yeah, if you want to compute that Facebook is the best way to do that. And it's very interesting because the first computation in 2011 was about 4 degrees of separation. And in 2016 was 3.5 degrees of separation. So yeah, that's a nice thing of this technology that allows us to do that very efficient. So the impressive thing is that in 2011, they were able to do that using these streaming methods, using only 1 machine. So, and that's for all the numbers of users of Facebook. This is very, very, very impressive. Okay, and then, yeah, how we can speed up things. So for example, a decision tree. So a decision tree, as you know, it's very nice method because it's explainable. We can understand how the decisions are made. And they are very powerful because when we combine them in ensembles, the resulting methods are very, very good. The problem of the decision tree is that it's not a streaming method, because when we need to decide how to grow the tree, we need to look at the data that is in memory and then use, look at what is the best feature to use to grow the tree. So this is why, there was this streaming decision tree that is called very fast decision tree. That the idea is that okay, when we want to decide if we grow the tree or not, if we split or not, what we are going to do is that we are going to wait to have new examples. Once we have new examples, then we decide if we split or not. So in this way, we don't need to store anything in memory. If we need to make a decision, we wait to new examples to arrive. Now, the question is how many examples? And for that, we use the halving bound, and this is why these decision trees are called halving trees. So it's very simple. It's a very fast decision tree that is grown, and trees are grown in a way that, yeah, when we need to decide if we split or not, we look at the difference between the benefits of splitting, and then we use this halving bound to decide if we split or not. So that's for one specific decision tree. What we did is that the random forest is a method that is very, very popular. So we built a streaming version of that, and we call it adaptive random forest because it's a streaming and it's adaptive. And yeah, the idea is very, very simple. So the idea is that we combine what is called bagging and random trees. So what are random trees? Random trees are trees that when we need to decide if we split or not, if we grow the tree or not, instead of using all the attributes, we are going to use only a random number of attributes. And this is how we grow. The thing is that the trees are not good because they are basically random, but the combination is much better than having a perfect tree. This is why these SAMOA methods are getting very, very popular. So here, for this adaptive random forest, we combine what is called bagging. It means that also we want the trees to be different. So what we do is that instead of providing the trees with the same data, we are going to provide each tree a variation of the data that is sampling with replacement. So it's from the same distribution of the data, but it's different data sets. And this is going to help also to have diverse trees that are different. And this is going to help to have a strong classifier at the end. And yeah, the thing of this random forest is that it works only with trees, right? And what we did is that we extend this to random patches, means that we can use it for any classifier. What we are doing is that we are deciding which random features we are going to use for all the classifier. And then, yeah, we build these different classifiers, we combine them, and then we get a good combination. So yeah, this is what is this streaming random patches. And it's very interesting because in terms of results, the results are much better than than using the random trees. It's the same idea, but at the end, it seems that at least in streaming, is working better. And finally, a method that is also very popular is based on nearest neighbors, so means in similarities. So there was this best paper award at ICDM 2016, that the idea was to have like two types of memory, a short-term memory and a long-term memory. The short-term memory is basically the last examples, they have arrived. And the long-term memory is where we try to, using clustering, we try to get what are the most representative examples that we are going to use for this long-term memory. And then using these two, we are really, really good and we can make very good predictions. Yeah, so what we did is that we put that into ensembles. So instead of using one model, we use several models together. And this, yeah, this gives a very good results. Okay, and yeah, just to conclude, just mention some open source tools. So as you know, Waikato is very well known internationally for Weka, the software on machine learning in Java, with more than 10 million downloads and more than 18,000 research citations. Yeah, has been the most popular software in Java. We have MOA that is like Weka, but is specific for streaming. So we are not storing the data. So what we are doing is that we are, updating the models continuously, and we are adaptive. So that's the main advantage of MOA. MOA also is in Java, and it's it's very close. It can connect to Weka, and it's quite good. We have this book at MIT Press that is called Machine Learning for Data Streams with Practical Examples in MOA. that is open available, so you can read it online. And finally, as Python is becoming very, very popular, we have now this River software package. So this is like a MOA, but in Python. So you can use it in notebooks, and it's also something that is, it's quite recent. I think we released that in 2020. And the interesting thing is that there are already books that it is not us, so it's someone else that already write the book in River. So that's very impressive. It means that it's becoming popular when other people write books about the software. So that's really, really good. And I think that that's a summary of what I wanted to talk a little bit about green AI, what green AI is. These two things, right? So work on green environmental topics, problems, but also at the same time how we do AI in a environmentally friendly way, energy efficient. And just to mention that we have this AI Researchers Association. That's we have this annual conference in last year, and we are also quite active on writing discussion and white papers. So we have this white paper on New Zealand strategic approach for the national strategy. But recently this year we launched this ChatGPT and large language models. What are the implications for policymakers? And finally, just that we are here to talk and discuss and help you. So remember that data is really the core. So we can talk about what is the data, what are the best algorithms, and how much computational power we need. And also, we are happy to help on growing capabilities and see what are the missing skills and how we can help you on this. So, thank you very much.
Thanks very much, Albert. Are there any questions online? I do want to acknowledge that you really try to cater for a very wide spectrum of audience, because we had a very nice introduction to the basics of machine learning, the artificial intelligence, but at the end, we sort of really had a glimpse at the cutting edge stuff that's being worked on, right? It addresses one of the biggest challenges with machine learning which is, of course, how do you improve on it without spending a massive amount of energy doing so every time, right? So while people may be thinking of questions, I have one. And so one of the questions when it comes to adaptive AI is how do you prevent your models from unlearning things that it could do, right? Because if you had a massive influx of data of a particular nature, right, it may completely skew your learning, and then it unlearns the things that it knew how to do. And toward the end, you talked about the SAMKNN, which is one way of sort of transferring some long-term memory to transferring short-term memory to long-term memory. But I do know that would be potentially difficult if you are dealing with something like a decision tree, or if it's so is there a limitation on what type of algorithms could be used with that approach?
Yeah, very good question. So I think that in practice, what is happening is that, the data may be changing continuously, and then something, we built a model, it's relevant right now, but then things happen, and then, but maybe then this, again, later on, we go to the same distribution of the data at the beginning. So I think the main approach then is to have like a pool of classifiers, have a different pool of classifiers, and then when something new appears, first check if it's something that was already before, and then we can reuse one of the classifiers and maybe improve that. Or it's something that is completely new, and then we really need to start collecting data and build something new because we haven't seen that before. But the key is this trade-off between forgetting, right, and learning, because we don't want to forget everything. We want to forget only the things that we are not going to use, but all the things that we can reuse, we would like to keep that in a way that we can use. So I think that what I have seen is that the people usually do that, having this pool of classifiers. Some people, they call it recurrent concept brief. So we can say that each model of the data is like a concept, and then what we do is that we detect the drift in the concepts, but then We have these recurring concepts. We store them, and when we see that something new is appearing, we try to see which one can be the best one to use.
Okay, great. Are there any questions online? If not, I mean, I think this is not really meant to be a seminar where people sort of understand, everything that TAIAO does, but it's really aiming to highlight the capabilities here at the university, both within the AI Institute, as well as those specifically facilitated through TAIAO.
Yeah.
And so, I do want to take this opportunity to acknowledge that this year we lost one of our giants in machine learning, and Ian Whitten, who passed away earlier this year. But we're very happy to see that machine learning research and application is still very much active and still on the cutting edge at the University of Waikato. And for people who are not at the university, for wherever you are, if you have research needs, now you know who to come to. And you don't have to be an AI researcher or a machine learning researcher. You just need to know your data. Come and have a conversation with people in the AI Institute. And this is why we're here. We're here to facilitate.
Exactly. We're very happy to buy you for a coffee and just talk about what's the problem, what's the data that you have, and then see what could be the best way to address the problem. Very happy to have these discussions and conversations, and
Wonderful. Well, I want to thank you, Albert, for spending the time to prepare this seminar. It's a little token of our appreciation.
Thank you so much.
Giving a ERI seminar. So if nothing else, then please join me in thanking Albert again for giving the seminar today.
Thank you. Thank you.